the most complicated type of matrix that we are going to use to represent a symmetry operation is going to be the matrix for a proper or an improper rotation. So let's, for example, look at a proper rotation, Cn. And we want to see what the 2 by 2 matrix representation of this symmetry operation will be. And it turns out to be a somewhat complicated formula. So So this is what it looks like as a 2 by 2 matrix. And we notice that we have complicated terms because we have cosine of an angle. So for any Cn, the cosine of the angle 360 degrees divided by n. The term in the first row, second column, is going to be minus the sine of 360 degrees divided by n. Down here we have sine of 360 divided by n, and then the next term along the diagonal is cosine of 360 degrees divided by n. So that's what it looks like in terms of degrees. Now if we write it more as a mathematician would write it, you can write it in terms of radian measure, in which case it looks a little more condensed. So we have cosine of 2 pi over n. We have minus the sine of 2 pi over n. Down here we have sine, so this is the positive sine of 2 pi over n, and then down here cosine of 2 pi over n. So this is how we can represent a proper rotation using a matrix. So we've done it in terms of the subscript n here. We can also do it in terms of just for any particular angle. So if you want to write the rotation for any particular angle, I'll just use the symbol R for rotation here. So if we have rotation as the function of some angles, let's say we're going to rotate an angle theta, and this is going to be a counterclockwise rotation. So you want to see how we can write that. So I'll put it down here also. In that case, we get a somewhat simpler expression. So this is for any generic angle, no matter what it's going to be. We have a rotation. In this case, the argument of each function is just simply going to be the angle theta. So we get a simpler version of the matrix if we just think in terms of the rotational angle rather than the how many fold rotation we have. So, but this is still going to be complicated depending upon which particular angles we're going to be rotating our object. So this is the general structure of it. Now, it turns out that we can define another quantity for any matrix called the determinant. And it turns out that one of the things we recognize if we find the determinant of a matrix like this is we get cosine squared plus sine squared equals 1. So we actually can derive an identity from that. But we're not going to need that quite yet. So this is the matrix representation. So next is we want to see what are the sine and cosine values for the most important angles of rotation that we're going to need. So one way that we can do that is, it's a very useful thing to do in general, is to sketch out the general structure of the sine and cosine function. So we can draw a coordinate system here, and we can immediately sketch out what the sine curve looks like. Because we remember that the sine curve starts at the sine of 0 is 0, and then we get a curve that kind of looks like this. And we know that both the sine and cosine, in fact all trigonometric functions, repeat every 360 degrees. So this is 360 degrees. Here we have 180 degrees. This point down here is 270 degrees, and up here is 90 degrees. So this gives us the general shape of sine of x. So this is the sine function. Now, once we have a sketch like this, it makes it quite easy to recall the sine of important angles. So for example, we notice that the sine of 0 is 0. The sine of 180 degrees is going to be 0. Sine of 360, just like the sine of 0, is going to be 0. The maximum value of the sine function is positive 1, so the sine of 90 degrees is going to be plus 1. Okay, let me sketch that in there just to remind us of that fact. That's plus 1. Down here is minus 1. By the same reasoning, the sine of 270 degrees is also going to be minus 1. So just by making a general sketch like this, we can determine and recall the sines of important values. If we want to replace our degree measure with radian measure, let me just do that so we have a version of that graph. Again, we recall that there are 2 pi radians in 360 degrees for one full rotation. So that would give us 2 pi here. At this point, again, 0 is pi. Up here we have pi over 2. And then this point down here is 3 pi over 4. In general, in chemistry, we're going to use degree measure, but in a mathematics course, we're much more likely to use radian measure. Let me just kind of clean this up a bit. That's pi over 2. There we go. So again, it's very useful for a student to be able to sketch the sine curve out quickly from memory. So that's the sine curve. Let's see about the cosine, because we need both sines and cosines to write down the exact forms of the matrix representations for the various rotations. So here we have our coordinate system again, and we recall that for the sine function, the sine of 0 is 1. So we actually get kind of a situation like this, and the important values of the function are going to be here and here. The maximum value of the function, of course, is positive 1. The minimum value of the function is going to be minus 1. Call this is going to be cosine of x. So let's see the other important values from the point of view of degrees. This point here is 180 degrees. Here we have 270 degrees. Here's 360. And here is 90 degrees. So we notice right away that in the case of the cosine function, that the cosine of 90 degrees is exactly 0. The cosine of 0 is positive 1. The cosine of 180 degrees is minus 1. The cosine of 270 degrees is going to be 0. And then it repeats again. So for 360 degrees is the same as 0 degrees. The cosine has a value of 1. And again, we can replace these values with the radian measure, just for completeness. It's very important if you're using your calculator to determine sine and cosine values. Be very careful whether you're inputting in terms of degrees or in terms of radian measure, because you'll get different answers. That's also why it's a very good idea to be able to quickly sketch out the sine and cosine functions, and it allows you to double check that the values you are inputting and getting out of your calculator are actually correct. So here we have pi, here we have 2 pi. At this particular point here we have 3 pi over 4, which is 270 degrees. For 90 degrees, that is pi over 2 radians. So this gives us a quick sketch for the cosine function. Okay, so now that we've looked at the sine and cosine functions and the general form of the matrix representation for rotations, let's find the exact values for certain important cases of the rotation function. So the first rotation function that we definitely want to look at and double check from what we know already is C1. So C1 is the same thing as a rotation of 360 degrees, or of 0 degrees, if you want to put it that way. So we can write down the matrix representation right away. So we have the cosine of 0 degrees. minus the sine of 0 degrees. We have the sine of 0 degrees and the cosine of 0 degrees. So here we're doing for C1 as if it's a rotation of 360 degrees. We already know what the form of this matrix is, but let's see that we get the same exact answer by thinking of it as a special case of a rotation matrix. Well, as we saw from our diagram, the cosine of 0 is 1, so we can put 1s right along diagonals. The sine of 0 is 0, and since the sine of 0 is 0, minus 0 is equal to 0, so the matrix that we get for a C1 rotation is going to be exactly the E matrix that we had done before, the identity matrix. So it's good to double check that we actually get this particular value when we think of C1 as a rotation. Okay, that's C1. So our next case, let's look at as C2. So C2 is going to be one of the most important rotations that we do. C2 comes up very, very often. So let's see what we get in those particular cases. So here we have cosine of 180 degrees, sine of 180 degrees, sine of 180 degrees, and cosine of 180 degrees. So let's see what those particular values are going to be. Well, one of the easier ones is we recognize that the sine of 180 degrees, if you double check in the video what the sine curve looks like, we recall that the sine of 180 degrees is exactly 0. So these terms are going to be 0 also. The cosine of 180 degrees is going to be minus 1. So we end up with a matrix that has minus 1s and 0s on it. And this is going to be the two-dimensional matrix representation for C2. Now you may notice right away that this matrix looks very much like the I matrix, the matrix for inversion. And in 2 dimensions, that's true. The matrices, by coincidence, happen to look the same. Once we go into 3 dimensions, we'll see that there will be a difference between the 2 matrices. Since they are distinct symmetry operations, we would expect that they're going to have distinct and different matrix representations once we get into 3 dimensions. And that's true. But so this is one of the most important of our matrices, which is the C2. Now, a second one we can look at is the C4 matrix. So for C4, we would expect that we need to find the sines and cosines of 90 degrees. Let's put that in there. I put it in different colors so it's a little easier to see. Okay. So now we want to see what these particular values are going to be. Now we recall that the sine of 90 degrees, remember the sine curve kind of does like this, sine of 90 is going to be 1. So that makes the minus sine of 90 minus 1. So we end up with a minus 1 in this particular position. Cosine of 90 degrees is going to be 0, and then cosine of 90 is 0. So we're able to come up with a matrix representation of C4, which looks like this. So we have 0, minus 1, 1, and then 0. And you'll notice something here that's of considerable importance. We notice that in C2, all the non-zero values were along the diagonal. So we had numbers along the diagonal, and we had zeros every place else. But when we get to C4, put C4 up there. When we get to C4, I notice that now I have numbers that are, we call off the diagonal. So that aren't along here, we have numbers that aren't 0. And that's going to have a important significance later on. Because it turns out that once I get to C3, we're going to do C3 in a couple minutes. So for C2, we have numbers along the diagonal, and that's all. Once we get to C3 and beyond, for any C with n equal to 3 or greater, we're going to have numbers that are off the diagonal. And that's going to lead to important mathematical and chemical consequences. So we want to make a distinction between C2 rotations and then C3s and beyond, because the C3s and beyond will lead to a phenomenon called degeneracy, and degeneracy will be one of the most important mathematical and chemical consequences of symmetry that we're going to see. But for the time being, you want to be able to derive and, if necessary, memorize the matrix representations in 2 dimensions for C1, C2, and C4. For C1, C2, and C4. Now let's look at the matrix that we can use to represent the C3 proper rotation. First, let's draw the XY plane. So we have a Cartesian coordinate system like this. And then we're going to judiciously choose to draw an equilateral triangle. In the second quadrant. And the reason for doing this is that we want to represent and find the trigonometric values for a 120-degree rotation. Because remember, a 120-degree rotation is the rotation that is involved in a C3. Another step that we're going to take to make life easier for ourselves is to make each side of the equilateral triangle have a length of 2. So that makes this side 2, and it makes this side 2. So as you'll probably recall from trigonometric courses that you've taken in high school and in college, that we often define the sine and cosine using a unit circle. Here, merely for convenience, we've chosen the length, the radius of our circle to be 2 rather than 1. And we'll see why we did that in just a second. But what we want to be able to do is calculate the sine and cosine. So the first thing we want to do is bisect this angle. And this line will bisect this side. It's a perpendicular bisector. So it's going to give us a right angle. And it's going to divide the base of the rectangle into 2 sides, into 2 lengths, each of which has a length of 1. So that's going to be useful for us. So once we've done this, we recognize that we have a triangle over here. One side is 1. The hypotenuse is 2. And so if we use the Pythagorean theorem, we realize that the length of the altitude for this particular right triangle is going to be the square root of 3. The square root of 3 squared is 3. The square root of 1, the square of 1 is 1. 3 plus 1 is 4. We take the square root of 4 and we get the length of the hypotenuse, which is 2. Now, having done that, we can use this construction to calculate the sine and cosine. So, for example, the sine, we recognize that the sine we can get from thinking of this as a particular point and looking at the coordinates of the point. We know that we can get the sine is the y coordinate. So the y value is the square root of 3 divided by the length of the hypotenuse, which is 2. Now recall to do this in symbols. That is the y coordinate, and this is the length r. We notice that r is equal to 2 in this particular case. So we see that the sine of 120 degrees is going to be the square root of 3 over 2. On the other hand, let's try to find the cosine of 120 degrees. So in this case, the cosine is the x value divided by r. Now, you can write down the r value again. It's going to be the same as it was before. It's going to be a length of 2. But now we notice that since our radius here is in the second quadrant, recall here's the first quadrant, here's the second quadrant, third quadrant, and the fourth quadrant. Since we're in the second quadrant, x is negative. So the x length here is -1. So we see that the sine of 120 degrees is the square root of 3 over 2, whereas the cosine of 120 degrees is minus 1/2. So these are among the first values that we've had that haven't been a 1, a -1, or a 0. So it shows that in the rotation matrix, we can end up having values which are not whole numbers. So we got our sine and cosine. So once we have this, we can actually write down the matrix for C3 in 2 dimensions. And recall that, so we put the cosine of 120 degrees, which is minus 1/2. And that goes along the diagonal. Up here in the upper right, we have minus the sine. So that could be minus over the square root of 3 over 2. And then in the lower left, we have the sine of 120 degrees, which is the square root of 3 over 2. So this is our C3 matrix in 2 dimensions. Now, one thing I had mentioned before, we can look at in more detail here, is that if I look, let's put this for some generic angle, so we're just doing a proper rotation of some generic angle, we had noticed that we can write it as cosine theta minus sine of theta, sine of theta, cosine of theta. And the feature that I want to emphasize is that the sine of theta, is only going to be equal to 0 if theta is equal to something like 0, pi, 2 pi. So it's equal to some integer times pi. And that's if we do it in radians. And if we think of it in terms of degrees, it's going to be 0, 180, 360 degrees. So that tells us that if we have a rotation of any angle other than 0 or 180 degrees, then the sine of theta will be a non-zero value. And we start to get these values off the diagonal that are not 0. Once we do that, we'll show this later, but effectively what happens is we start to mix together coordinates. And this mixing of coordinates leads to certain interesting features. And let me just demonstrate this mixing of coordinates with the C3 rotation to show more clearly what I'm referring to. If we want to see the effect of this rotation on a particular point, we had already mentioned that we can do this by matrix multiplication. Now, when we multiply the matrix times the point, we end up getting as an answer the new point. Basically, it takes xy and it moves that point to some new point, x prime, y prime. So let's see what we get if we do this. And we see something very interesting about what happens. So let's multiply. We have our first row. And our first row is here. And we multiply the first row times the first column, so that what we're going to get is an expression that looks like minus 1/2 times x minus the square root of 3 over 2 times y. So that's what we get multiplying the first row times the first column. So now for the next part, we look at the second row, the matrix, and the second row will multiply by the first column. And we're left with an expression that looks like the square root of 3 over 2 times x minus 1/2 of y. Okay, and this is the new point that we get. And let me just simplify this just a little bit to make it look a little nicer. So we get minus x over 2 minus the square root of 3y over 2. And then the y coordinate is going to be square root of 3 or 2 times x minus y over 2. Now the important thing to see here is in a C3 rotation, what used to be the x coordinate, to get the new x coordinate, it involves what the old x coordinate used to be, but also what the y coordinate does. So to see how x changes, not only does it depend upon the x that we started with, it's going to depend on the y that we started with also. This is why I refer to this idea of mixing of coordinates. So in the new x, in x prime, we have both the old x and the old y. Similarly, to find the new value of y, y prime, it involves what the old y used to be. That's our y without a prime here. But it also depends upon what the old x value was also. So we see that to get the new x and the new y coordinates, we have complicated expressions that involve both x and y. This will not be true for a C1 or a C2 operation, but will be true for C3, C4, C5, on forever after that. So we see that there is a fundamental difference which occurs once we get to C3. So when we are examining a molecule and we're looking at its symmetry operations, one of the most important things that we need to do is to identify all the rotational axes and then classify which of those rotational axes has the highest order, which has the largest number here. So this is a third order or a threefold rotation. The bigger that number is, the more important it is. And we want the high order rotation axis, that's the C sub n, that has the highest value of n. If that n is 3 or greater, there are certain very important chemical consequences which will accrue based upon that being present in our molecule. So we looked at C1, C2, C3, C4, and mirrors the identity and inversion in 2 dimensions. In the next video, we're going to go completely to 3 dimensions because 3 by 3 matrix in general will be the largest and most complicated matrix that we will have to deal with in our use of group theory, and we will show how we write the 3 by 3 matrix versions of the symmetry operations that we've already examined in 2 dimensions. In 2 dimensions.